At me, and then you just see me snap out of me.
Here's a bunch of papers for you. Thin those around.
And I don't even remember it. I took out 4 cards and I didn't remember it until they showed me what it was.
All right, well, I guess it's time to get started again, even past time to get started. So welcome back, and I was just looking at the schedule for this class this week and following into next week. And so just in case you haven't been, what happens Wednesday, not 2 days from now, but 9 days from now. Test 2 is coming up here, okay? And so as I was looking it over, and of course, maybe I should just remind you then, Test 2 has chapters, I guess it's 5, 6, and 7 and 8. And I even grouped those together, as you notice. So we did 5 and 6 for a long time, a lot of examples. And now we're getting started into 7 and 8. And I thought today might work best if I just kind of group them all together. So we'll do the rest of the lecture here on 7 and even tie that together with 8. There's no point in really kind of separating it. Bad part about that is maybe I don't do any examples, but I think by the day's over, I'll get a chance to do examples. Maybe not, but so here's the plan. Finish the material in terms of lecture of 7 and 8, kind of grouping them together. Then on Wednesday, do examples from chapter 7. On Monday, do examples from chapter 8, and hopefully that will put us in a perfect position to have the exam on Wednesday. So don't let it get away from you. And get working on these. And I know this time in the semester can get very busy. And you have a tendency to put things off and say, well, I'll get to it when the test comes. Well, okay, test is coming, so get to it is, I guess, my warning for you here. So that's the idea. So let me keep talking here about chapter 7. And like I said, it flows well into chapter 8. And I'll just, like I said, just kind of group it together. I was kind of looking at the material going, you know, I really should. I'm just gonna tie it all together. And I would want to start with a diagram that you've already seen and add to that diagram. We've been looking at this diagram for a while. This one here that says, how is position related to velocity? How is velocity related to acceleration? How is acceleration related to the net force? And how is net force related to the individual forces? And so in this diagram, I was trying to give you a mental picture of, here's what we did first. This was our first test. This was chapters 1 through 4, where we looked at the relationship between speed, velocity, and, well, I guess it's position, velocity, and acceleration. Then as we got into 5 and 6, we tied these together. And that was Newton's laws of motion. And so we had Newton's 3 laws of motion. We talked about them in 5, more of a review since you've seen them before, but now applied them on a little higher level in 5, and even so much in 6, because in 6 now we added turning to it, we added air resistance, and we added accelerating reference frame, non-inertial reference frames. So we spent a lot of time on that. But then we get now into chapters 7 and 8. And you might remember, this is where we left off on Wednesday, was this, that the work, and we put here the total work, would be equal to the change in kinetic energy. And so we had a discussion here, and we even called that kinetic energy, so this might be final minus initial or change in kinetic. I don't think on Wednesday I got a chance to write it on the board this way, but this is what I referred to as the work energy theorem. And that there is a connection then between the work you did. And so we looked and we kind of left the day saying, well, what if there is positive work? What if there is negative work? And positive work means it would be going faster at the end compared to when it started. Negative work meant that it's going slower at the end than when it started. And zero work means it's going the same speed. And so we had our little diagram about positive work, negative work. And so we looked at the work individually. And the example we had was that block, if you remember. My hand was pulling on it. My hand did positive work. The friction did negative work. The question is, when we total them, which one was bigger? If my hand was more positive than the friction was negative, we would have positive overall work and therefore it'd be going faster. And the reverse is true the other way around. So I want to pick up right here on this work energy theorem, because it's the work energy theorem that then leads to conservation of energy, and that really kind of sums up all of chapters 7 and 8. The answer to 7 and 8 is really conservation of energy. And so I'll joke with you again. I already gave you all the answers to 7 and 8. To 5 and 6. You want all the answers to 7 and 8? Conservation of energy. There it is. Just fill in the details. Okay? And so we're back to that very idea of just some simple fundamental ideas explain the universe of phenomena. Well, I wanted to finish this diagram to get started here. And so the thing to add here, and you begin to see it, if I put on the board maybe above this diagram, this concept of work, and this pen looks like it's getting a little dry here. I'll try a blue one here. But if we look at work, or if we look at the idea of energy, I hope you're seeing here that here's what we have, is we have a connection to get to velocity by using work and energy. And so not worrying about Newton's laws of motion, we don't have to say look at the individual forces and add them together to get the net force, to get the acceleration, to get the velocity. What we can look at then is the work, which still is tied back to the individual forces, but it's got the integral in it, the work energy theorem in it, and we can get speed. And so keep that in mind, giving you a second option, and that's probably the best way to describe it. This is a second option of how do you get the velocity of an object. Okay? And in fact, if it helps you think about it, remember this. This was my clue to you in Physics 102. If the question is, what is the velocity after, and if they say something about time, then they're dealing with accelerations. And so how fast is the object going after 3 seconds probably implies that I'm going to get that with Newton's second law of motion. I'm going to look at the forces. I'm going to add up the forces. From that, I'm going to get the acceleration. And from the acceleration, I'm going to get the velocity. And so that's kind of your clue. What is the speed after 3 seconds? But there's another way of asking that same question. What is the speed after 3 meters? You know, so something is happening. Well, now they're talking about distance. And when they talk about distance and forces, hopefully the stuff we're learning now clicks in and says, oh, this is energy. This is conservation of energy. This is the work energy theorem. And so that's your connection. So keep that in mind. This is another approach, if you will, of how can you get to velocity. And as you'll see, it's not the only thing work and energy can give us. Work and energy, as we'll soon see, can be tied back to forces. So you may not know the forces, but if you know the energy, then you can work the other way and get the forces. And so that's an important step in here too. And so I'll put up here it is. Here's our chapter 7 and our chapter 8. And so there's our diagram so far. Chapters 1 through 4, chapters 5 and 6, and now what we're doing 7 and 8. And so we're all doing this mechanics, of course. That's why this class is called mechanics. We'll never leave mechanics this semester. But we're all looking at mechanics. And so there is the tie-in and for this next 2 weeks and before we get to the test. And then after that, we'll worry about after that when we get to after that. But there is our tie-in. All right, well, keeping that in mind then, I want to pick up where I left off. And this is where I left off, the work energy theorem. And so we went through and we talked about what work is. We looked at some positive numbers and some negative numbers. It's a very simple example. More examples here to follow, but if you dig a little deeper back, maybe go backwards here, remember where this came from. This came from the net force dotted with some distance is equal to the change in kinetic energy. That is a final kinetic energy minus an initial kinetic energy. It's at this point where your author kind of breaks it down and says, now let's look a little bit closer at this. And he defines, although really he doesn't divide it into chapter 8, so that's why I said I'm going to kind of take where we are with 7 and tie it with 8 a little bit here. But he really starts here and says, you know what, when you look at forces, you can really put them into two categories. And there is what we would call a conservative force, and then another category which we might call a non-conservative force. And what's the difference? Well, not really too much, although I'll define the difference here in a second. But why he separates them is you'll see it's easier to work with conservative forces than non-conservative forces. And I think that's why he's broken it down into these two chapters. So he says, look, in chapter 7, let's only deal with conservative forces. And then let's add to that as we get into chapter 8. So I'll throw the both up there, something like this. I'll say, let's take this integral and separate it into forces that are conservative and forces that are, well, maybe I should put non-conservative. And that equals the change in kinetic energy. Now, those sound like big fancy words. I mean, let me give you the definition of conservative. And basically the author says, look, a conservative force is this. It is what you would call in math path independent. That is, it doesn't matter what path the object takes, you're going to get the same amount of work. I mean, let me step over here to the side here and say, look, what if I have an object at point A, and that object at point A gets over here to point B? Well, in its path from A to B, there may have been some work. There may have been some forces. If there is, we would have to do the integral. Maybe the object just went straight like this, kind of a straight line, maybe a slope down. Maybe the object went like this. It went horizontally first and then vertically first. Or maybe the path was really complicated. It dipped down, went up, came back down, went below, leveled out, and then came to B. And so if I call this first one path 1, the second one path 2, and the third one path 3, then each of these works, work 1, work 2, work 3, would have to be some kind of integral where we would have to pay attention to the path. However, what is meant by path independence here, right here, for a conservative force is it doesn't matter which path you go on. If it's conservative, you're going to get the same amount of work. All right, why do we care about that? Well, here's why. Let's say this is a roller coaster. And one of the forces that are conservative, as we'll mention here, is gravity. Gravity is a conservative force. Well, we'll show that in a minute here. But why is that helpful? Well, it's very helpful because if you think about how much work is done by gravity, and this is the roller coaster ride, it goes down, it comes up, it goes down, it comes back up, it levels off. That could be a hard integral. Isn't that a complicated path? Wouldn't it be nice if the path was simpler than that? Wouldn't it be nice if you could just go horizontally to here and then vertically down to here? Wouldn't that be a much easier integral? And if it comes out to be the same number, wouldn't that be the appropriate way to do it? So in other words, the roller coaster may really actually go along path 3, but path 3 may be a hard integral, 1 or 2 may be an easier one, and one of those may be easier than the other. Wouldn't it be better to do the easier one, even though the roller coaster didn't actually make that path? Yes. And so that's why the author introduces, at this point in chapter 7, conservative forces, and he leaves non-conservative forces until the next chapter and says, wow, whoa, if we get into the next chapter, then depending what path it takes does matter, then you have no choice. Don't you have to do the integral along path 3? I mean, that's just what you have to do, because that's really the path it takes, and any other path doesn't give you the same answer. So again, that's why we kind of divide this into 2 categories. And if this is a roller coaster, you can see that maybe the question is, the roller coaster is at A with some initial speed. It's going to get to B at some final speed. Coming back here to the work energy theorem, can you kind of see here, if I can figure out how much work is done on that roller coaster, couldn't I find the new speed of the roller coaster? I mean, if I know what speed it has at A, couldn't I then find the speed at B? All I need to do is figure out how much work is done. And that's what this is. This is the work. And if the work is done by gravity, gravity being conservative force, let me not worry about path 3. Let me just integrate path 2. I know the roller coaster went on path 3, but so what? It would have the same amount of work done as if it went path 2. And as you'll see, path 2 is going to be a much easier integral to do than path 3. So, again, perhaps a little bit abstract, maybe too abstract here for it to really sink in. Until we get to some examples, you'll really see the advantage here. But this is why the author says gravitational forces are great. They are path independent. And even though something makes a very complicated path, again, like this roller coaster, we're not going to actually do the integral that way. We're going to do the integral this way. We're going to do it with number 2, or we're going to do it with number 1. And so forces involving conservatives are much nicer. Now, non-conservative forces, well, probably the best one to give you right now is friction. And I think that's all we'll see this semester. When we get to E&M and next semester, or next fall actually, we'll see other non-conservative force. But right now, we'll just say, hey, non-conservative force, that's friction. So again, kind of just looking at this roller coaster as an example, you would see then, to calculate the new speed of this roller coaster, to calculate its work, I've got to separate it into 2 calculations. How much work is done by gravity and how much work is done by friction. The one for gravity is going to turn out to be the easy one, because we won't actually do an integral with the path it takes. We will do an integral with path number 2. So that's the idea. Unfortunately, with the friction, we have no other hope but have to do path number 3. The answer does depend on what path it takes. So that's why we separate it. And in fact, let's just kind of separate them and give them some names. Your author then says, let's do this. This integral here, we will call then the negative of the change in potential energy. And so this becomes our definition of potential energy, a final minus initial. Or to put another way, the definition of potential energy is, negative of the work. Okay? And that's how you'll see it in there. This is the work. Now he puts a little sub C to say this is the work done by a conservative force. Okay? But as I was saying, that's all he introduces in chapter 7 is conservative forces. Let's give a name while we're here. I probably won't deal with it until we get into chapter 8 here. But as long as we're here, we might as well add this second piece. And this second piece is going to show up as an energy. And so this will be our heat energy. It's usually a Q. It's or negative. And so we will say the work done by our non-conservative force shows up as a different type of energy. Shows up as a heat energy. And so now you begin to see the three energies that I think you're already acquainted for. These were the three we talked about in Physics 102. A kinetic energy, a potential energy, and a heat energy. In fact, just last week we got done with the 102, and when I was talking with them, I was thinking about you guys. I was saying, oh yeah. So my 121 class, we'll do this next week. And I remember when they were in the 102, and we just kind of threw it out there with no calculus and no integrals and that kind of thing. But you could now begin to see where conservation of energy comes from. Watch what happens then when I move these to the other side of the equation. Let me take two steps. The first one then would be a change in potential energy minus a heat energy is then equal to a change in kinetic energy. And if we write that out then, this would be minus a final energy minus an initial energy. This would be a heat energy. This would be a final kinetic minus initial. And if I rearrange this equation so that all the positives are on one side and all the negatives on the other, we have a very powerful principle that I know you already have seen. You wouldn't be this far in your education if you hadn't heard the word conservation of energy. But it begins to show here where it says the final kinetic plus the final potential energy is equal to the initial kinetic plus the initial potential, and then plus heat. And so this is our conservation of energy statement. This is saying here that, all right, take whatever energies you start with, that has to equal to whatever energies you end with. And again, the only difference between then chapter 7 and chapter 8 is whether or not you're going to throw any friction in there. Is there going to be any non-conservative forces? So you'll see as we get to some examples, in chapter 7 we will have just kinetic energies and potential energies, and then over here in chapter 8 we'll have then some friction thrown in there. But the bigger picture, and that's why I decided today I'm going to lump it all together so we can just kind of keep that big picture going, is that take all the energies you start with and set it equal to all the energies you end with. All right, so here's that pathetic joke. You want all the answers to chapters 7 and 8? There it is. Right, it's got a little box around it. I can guarantee everything you do in chapter 7 and 8 is right there. It's a conservation of energy. The energy you start with is the energy you end with. So I can guarantee that, any problem, if you start right here, now granted, you might have to fill in a lot of details. It may be 2 hours later before you finish the problem. Okay, but that is the answer to each of those problems. Conservation of energy. So, I guess I've just given away all the answers to the test, right? Newton's second law of motion right here. Well, maybe I'll put it up here again. Sum of all the forces equals mass times acceleration. So there you go. There's all the answers to 5 and 6. There's all the answers to 7 and 8. That's what the test is on. We might as well go home and rest until we have the test in 2 weeks, right? That's it. You got the answers. Okay? So, and as you know, that's where it gets hard. It's, again, back to our syllabus here, It's not about memorizing a bunch of formulas. It's, can you take these very simple, powerful, fundamental ideas and apply them to a universe of phenomenons, and we'll have roller coasters, and we'll have asteroids, and we'll have molecules, and we'll have black holes, and we'll have all kinds of different things as we go to solve this. And we just got to take this idea and apply it. So, conservation of energy. In fact, maybe this might be a good time to put a plug in here for, if you remember your mechanics from the Physics 102, I tried to express to you that there's really kind of 6 things we're trying to learn. And so that could be said this semester too. There's only 6 things we're learning. Newton's 3 laws of motion, and then the 3 conservational principles as they relate to mechanics. So, we've done the Newton's 3 laws of motion. Now we're about to jump into the 3 conservational principles. And this is the first one, conservation of energy. You wouldn't surprise you, although don't worry about it because it's after the test. Conservation of momentum's coming up next. And probably not going to surprise you after that, conservation of angular momentum. Good. Some of you remember there from 102. So there's the 3 conservational principles and Newton's 3 laws. And if you know those 3 or 6 basic principles, you can explain all the motion. Everything about mechanics can be worked out from there. And that's why it's easy to stand up here and say, hey, you want all the answers to all mechanics? There it is. Newton's 3 laws, 3 conservational principles. Everything else you just got to fill in the details. It could be a lot of details and could be kind of complicated. That's why we spend time talking about them and working on it. So, let's keep working on them here. There's some interesting consequences here. First of all, when it comes dealing with this roller coaster, obviously then dealing with these energies become an important part, right? So let's talk about all of these individually. If we're dealing with the roller coaster, I'll start with the first one. That's probably the easiest one because we already dealt with it last time. I mean, what would be the initial kinetic energy of the roller coaster? Yeah, so we worked that out from Newton's second law. We did an integral, so let me not do it again, but there it is. So that would be 1/2 mv squared. Now it would be initial velocity because that's initial kinetic energy. Remember this, it came from an integral. You don't need to do it again. That's the beautiful thing of these chapters. If they are path independent, I can do the integral for you right now and you don't have to do it again. So don't go back to, ooh, what's this? Integral of net force dx. Net force is ma dx. A is m dv dt dx. That is the integral of mv dv. That is 1/2 mv squared. Don't go back and do that. You don't need to. I did it for you. I just did it again a second time for you. The author does it for you. So again, the real power here, and why I said to you guys earlier, I think you will find chapters 7 and 8 easier than what we did in 5 and 6 because we're not dealing with vectors. We're dealing with scalars. And we're not dealing with too many integrals because they've already been done. They're path independent. And so notice that this is the formula you get regardless of what the acceleration is. Regardless of what path it took. This is what it came out to be. I didn't say anything about the path or anything about the acceleration. And I got 1/2 mv squared. And so that's kind of the neat thing about it. Well, let me continue on. Let's go to, maybe I'll jump to the other side of the equation. Because again, this is really the same one. I mean, if this was a roller coaster problem, how would you put into that little formula the final kinetic energy? Well, that's the same thing, except now we're talking about a final speed. Okay, so it's a 1/2 mv squared. So maybe that's the obvious one. But the one I really want to begin to talk about is what would you put here for the initial potential energy? And that's what's new this morning is, wait a minute, how do I get potential energy? Well, this was our definition of potential energy. It was an integral. And it was path independent. So I'll tell you what, let's do the integral now. Never do it again. It won't matter what the path is. Even if the roller coaster goes on path 3 or even some other path, let's just look at path 2. And if we do path 2, we're done. And we don't have to ever do it again. We can just look at the results from path 2. And so let's look at it. Now I am going to add one little thing because I am going to put a little g down here. I bet you might guess what the g's for. Yeah, gravity. Because when I'm talking about the potential energy, I'm talking about which force? Yeah, the gravitational force. Are there other forces besides gravitational forces? There are. And I'm not talking about the frictional force. We talked about that, but that is a path dependent. Would there be other forces that could be conservative besides gravity? Sure, and it sounds like some of you know it already, or you've been working ahead in there. Springs is another good example. We often refer to it as an elastic energy. And so maybe we should put that in here. Maybe we should put what is the initial energy. It kind of looks like a V. What is the initial spring potential energy? So your author puts a little S there. Because in this chapter, he really only deals with two conservative forces. The first one is the one I want to deal with, gravity. Then the second one is the spring. You probably noticed over here, there is a set of springs. Oh, they're even red, white, and blue. So they're patriotic springs here. Okay? And so we probably need to take a moment and look at springs for a while. But in case I lose you in the ideas that are very deep about conservative forces and non-conservative forces, because that's a general statement that we want to see again and again when we get past mechanics. But let's just get through this semester. So if not worrying about the fancy name conservative and non-conservative, just look at these are going to be my two conservative forces, a gravitational force and a spring force, or an elastic force. This is going to be my one and only non-conservative force this semester, friction. And once we start learning how to deal with those, then in future semesters, we can deal with other conservative and non-conservative forces. Because we will have magnetic forces and electrical forces and nuclear forces coming up here. And some other non-conservative, well, those were conservative, but then some non-conservative forces too. So at the risk of losing you, here's what I'm saying. Two conservative forces. So how many different potential energies will we have? Two. How many different equations for heat will we have? Just one. Right? Unfortunately with this one, being path dependent, we can only write it as an integral, and we can't do the integral until we get that problem. So fortunately, this one is path independent, and our kinetic energy is path independent. So those, we can just come up with some algebra. And it's the only integral we'll have to think about is what if it is, the non-conservative force. Well, let me go ahead and for completeness put the final gravitational potential energy and the final spring potential energy there too. But that's really what this statement comes down to. This statement is, what are your kinetic energies and what are your potential energies? And maybe I jumped too far, because when it comes to the example I was talking about, a roller coaster, there's no springs up here. But there could have been. I suppose this could have been a spring right here at the end, and the roller coaster comes like that and then bumps into the spring. Actually, that'd be a fun roller coaster ride, I think. Just come in, hit the spring, then it shoots you back. Go backwards. Kind of a little reverse ride there. Although the spring may be too much of a stop, so I don't know if that would. I don't know. I mean, you'd be like, it could be a significant one. I guess that Superman ride at Magic Mountain's kind of like that. It's not. They don't use a spring. They use gravity. You go racing out, and then you go up, and do that. So you go one way, it slows you down, and goes the other way. But anyways, you'll see that in some examples. So we'll need to ask ourselves, is there a spring involved? Is there gravity involved? Because some problems will have, gravity and no springs. Other problems will have springs and no gravity. It will just be a level road. So again, I'm trying to give you the overall big picture here. And so what are we going to have? And basically this means that you really have, I think, is that 7 different terms up here? Because you're going to have kinetic energy and you're going to have 2 here. So there's 3. Then you're going to have final kinetic energy and 2 more. That's 6. And then heat. That's 7. And so there's our conservation of energy. These over here equal these over there. All right, well, I told you I would do the integral here and give you the equation for gravitational potential energy. So let's do it. Let's actually then look at what is the potential energy as you move from, say, point number 1 to point number 2 here. Well, maybe I'll go back here to this roller coaster and say, all right, let's look at this integral. Now, fortunately, we could go along any path, but if I put here that, I guess I just erased it, the definition, the negative of the change in potential energy, that is negative of the final minus the initial, is equal to this integral of f dot dr. Then we can actually do this integral. And in this case, looking at this roller coaster, let's go from A to B. Now, here's where you can see this idea of path independence can come really strong. Even though the roller coaster may go along this crazy path 3, I'm going to do the integral along 2. And so let me put maybe a little mark out here as C, or a point C, so that what I have is an integral from A to C, and then an integral from C to B. And so as I put in the force of gravity, and I'll put a little g even here, g, because I'm looking at the potential energy due to gravity. Still got to talk about springs too, but there's my gravity. And then the same thing, my gravity from C to B. Well, let me do the A to C. I can work it out if you want. I'm kind of hoping you see the physics without me working out the math, but if not, I'll work out the math. What is the integral there? What is the work done from A to C? 0, right. Why? Yeah, it moves horizontally. Which way is the force? Down, and that's what we said last time about the work, right? It's how much of the force is in the direction of movement. And so you might, write it this way, if you will. From A to C, I've got the magnitude times the movement times cosine of. And maybe I should just pause right there. We did this very close to the end last time. This is our dot product. If I put two vectors, A dot B, that would be the magnitude of the first times the magnitude of the second times the cosine of the angle between them. So that's what I'm doing here. I'm saying, what is the magnitude of the force of gravity? mg. What am I moving? The magnitude of my distance, dx's. What is the angle between my movement and my force? 90 degrees. And so as you guys correctly saw right away, there would be no work along this path. All right? How about this one, C to B? Well, again, same idea. The force of gravity is mg. The movement is in a downward direction, so I'll do a dy in this case now that we're looking at C to B, so we're going to move this way. And then the angle, what is the angle between my, I guess my two vectors, my force is down and my movement is down. So I guess that would make 0. And so this should come out to be mg, and if I do an integral, it's y, evaluated, of course, from C to B. So you might say it is mg, and the value of y at point B minus mgy, and its value at C. And so if you kind of look at this and you bring it back to this statement here, then this would be a minus of the final potential at G, and I'm going to do a distributive property here, and then plus an initial energy at G. And so if I kind of match the terms on the left hand and the right hand side, what you're saying here is the initial gravitational energy is mg at, wait, B? I don't like my sign here. Did I make a sign error? Let's see. The roller coaster went down. So which would be bigger, B or C? I guess C is bigger, which is good. That's saying my change in energy is 0. I mean, my change in energy is negative. Well, I guess I did down because I did right here. Oh, I see my sign error. Oh, a little subtlety here. Ooh. Ooh. I'm wondering if I should redo it or just tell you what the sign... I guess I'll just tell you what the sign error. I didn't notice it at first. A little subtlety in the math. It comes back to the dot product. Doesn't this dot product mean magnitude times magnitude? So these have to be two positive numbers. And then cosine of the angle. And I didn't quite do that here. I was a little careless with my math. When I go down, isn't the dy then a negative number? I mean, this really should have been written then as the absolute value of mg times the absolute value of dy, but since that was a negative number, I need a negative out there. Probably would have been better off back here to have said that the force of gravity is 0 in the I-hat direction and negative in the j direction. So then when I dot it times a dx in the I-hat direction and a dy in the j-hat direction, what I get is 0 dx minus an mg dy. And so that was our other dot product, which was taking the x components and putting them together, and then the y components and putting them together. So I'm not sure which is an easier way for you to see that there should have been a negative there, which would have made that a negative and that a positive. I probably should have had the roller coaster go uphill, and I wouldn't have had this math problem that I got to correct in the middle, because I might spend too much time here correcting the math and then missing the point. But maybe it's good that you see whether you do the dot product this way using the component, or whether you use the dot product this way and you do the magnitude of it. I do need to be careful, and without saying the magnitude, I wouldn't have put a negative sign there. And so dy down are negative numbers. All right. And when once I do that, then if I compare the negative signs together, what I have is the final gravitational and the initial gravitational. But what I want you to see here is this is an mgyb. And so in other words, the final gravitational potential energy formula is mgy. That's what I was after. So there's how we calculate gravitational potential energy. It's an m, a g, and a y. How high is it? So if it's at a final position, it would be the height of B. If it's at an initial position, then it is mg times y initial. And I would even go as far to say that the vertical height of C is the same as the vertical height at A. So again, you have that same formula. So you just need to put in the y for the final position and the initial position. So getting what I wanted you to see here, I now have this next statement here of this would be mgya. And this would be an mgy b. Pardon me? I's? Oh, okay, okay, you like that? Sure, okay, so y initial and y final. That's probably, yeah, that's probably better. That way, initial energy goes with initial position and final energy goes with final position. Yeah, that'd be easier to remember. I like that better. So again, in this first hour, that's what I wanted to show you. I wanted you to show you this here, like I said, conservation of energy in its full glory. That is the whole point here of this chapter. And like I said, the difference between 7 and 8 is 7's just going to do this. And it's going to look at potential energies and kinetic energies only. Whereas then in 8, we'll throw in some frictional one. Okay. Now, I know this problem does not have a spring involved with it. But if there was a spring, shouldn't there also be a formula here? And so I'll say the same thing, that it's kind of nice to do these problems because they are much closer to plug and chug problems than we've seen all semester. He's like, hey, there's the equation. Hey, there's the variables. Hey, put them in. Get out my calculator. Punch it out. Get the answer. Because there's not too much algebra. There's no vectors. There's no integrals to do. It's just algebra here. You put those in there. And so, like I said, you see the formula for kinetic energy. Don't do the integral again. I've done it. Now you see the formula for gravitational potential energy. Don't do it again. Solve the problem using the results that they are path independent. And so there's the mgy. And likewise for a problem that has a spring. Spring are also conservative forces. So let's do all of this again for a spring. And again, we'll have a formula. And once we have a formula, we can put it into here. And so I'll put it right here on the board. What is the formula for the spring? Now that one, we've got to talk a little bit more about springs. So I'll clear the board right here and say, okay, let's look at the change in potential energy again. And we'll do exactly the same set of integrals. And I'll even remind you, now that I've done the integral, don't you do it again. We're going to have a formula. It's path independent. So you don't have to do the integral ever again. But we do need to understand where it comes from. Otherwise, we run into troubles later on. But here's what I'm going to say. The change in potential energy of a spring is then negative of the final energy from a spring and then the initial energy from a spring, which means that would be an integral of the force from a spring dotted with the movement of the spring. Well, that's where I need a pause, and that's why these springs were put up here. What is the force from a spring? And maybe some of you remember this from 102. It was discovered by Hooke, so we call it Hooke's law. It is kind of a nice simple relationship. It's not a constant force, so springs are more complicated than gravitational forces. But there is a nice simple pattern here. In fact, maybe you can begin to see the pattern. That's why I put some of these weights here. Why don't I start off by putting a little bit of weight on each one to kind of stretch them a little bit here at the beginning. I'll even make a mark at their bottom edge here, here, and here. And then let me put 500 grams more on each of them. And you will probably notice something. All three of them have a pattern that they stretch further when you put more weight on them. Okay, what does that tell you? In other words, do you always get the same force from a spring? Does the force matter how much you pull it? Yeah, do these forces produce the same force as they did a moment ago before I put the weight on there? No, wouldn't you agree that now I've put more weight, now they're applying more force? I mean, the fact that they were balanced with a lesser weight meant that back up here, they had enough force to balance that weight. Now that they are stretched a little bit longer, but they have more weight, now they're producing more force. You'll see that again if I put another 500 on here, and another 500 on here, and another 500 on here. You'll see that it comes down to here, and comes down to there, and comes down to there. And so again, more weight, and the spring then can handle that more weight. As it stretches longer, that must mean it must have more force. So what we're seeing here is hopefully a pattern that does something like this, that here's the force, and here is the stretching distance. Will it be okay if I call it X for stretching distance? Because that's what your author does. I know that I've hooked up the springs in a vertical direction, so I'm tempted to put a Y here for that reason. But I think we're better off to put an X, since that's how your author discusses it, and we want to get the same formula as your author, so that hopefully my formulas on the board are the same as your formulas in your book there. And so the tradition has always been in the X direction here. I'm just using the vertical direction to illustrate it. But I think you can see then that there is some kind of pattern that when X is big, the force is big. So up here, I have some force. And then over here, when the stretching is small, the force is small, right? And so that's the first thing to notice, that springs are a bit more complicated than gravitational force. Gravitational force was just mg, period. What if the object was up here? Well, force is mg. What if the object down here? Force is mg. And so the easy cases were constant force. In fact, I'll be the first to tell you that if you were only dealing with constant forces, this probably is a waste of our time. Because wasn't it easy to deal with constant forces? I mean, constant forces, you add it up, you got a constant net force. Constant net force gave you constant acceleration. Constant acceleration gave you those nice 4 little constant acceleration kinematic equations. Those were easy. Well, the problems that got hard is when the force varied, because then the acceleration varied. And so remember our little diagram over here. If you're going to find the velocity, but it's a varying force, you've got to do an integral here. If I go here, the integral's already done for me, even though it's a varying force. And so again, integral's already done. It has to do with position. You see that, use the work and energy. All right, so there's point number 1, that springs do not give you a constant force. They do change. Now, how do they change? And that's what we call Hooke's law. Did you notice that each time I put 500, it's stretched by the same amount? So as I doubled the weight, I doubled the distance it stretched. If I tripled the weight, I triple the distance, right? You'll see it again if I put some more on here. I think this one goes too far and goes off the bottom. Well, maybe. No, well, right there, okay. Okay, so there's that one. If I put this one on here, you'll see this one stretch to here again. And, oh, I'm out of weights. Let me steal one off of here for a moment. Put it over here. If I put it here, I'll do that. And if I then take them apart so that you can see all the stretching that has gone on, it doesn't matter which of the springs. I'm hoping you still see that same factor, that didn't it increase by the same amount each time? And I don't mean that each of the springs increased by the same amount. What I mean, if I look at just the red one, it increased by that much, and that much. If I look at just the white one, it increased by that, then that much more, and that much more. If I look at the blue one, it increased by that, and like that. So each spring seems to have a pattern, what we would call proportional, right? You double the weight, you double the distance. You triple the weight, you triple the distance. And so what a proportion looks like on a graph then is this, right? And in an equation means that the force is equal to some constant times the distance you stretched it. And so this is our proportionality constant. This is what we are going to call the spring constant. Because although each of these springs, the red, the white, and the blue one, illustrate that the forces get bigger as you stretch it, they also illustrate that they're proportional, but they also show that it's not the same proportions. Each spring has its own uniqueness. So I can write down this formula for any spring. In fact, I like to put a little sub S there for this is the equation of the force from a spring, and it is a Kx here, and it has some kind of slope to it. But if I were to do this for each of those, I would have a slope for the red one, a slope for the white one, and a slope for the blue one. They would all have their own spring constant. So that's where they're different. So the point is, do all springs have stuff in common? Yes, just like all humans have stuff in common. But are all humans a little different? Yes, just like all springs are a little different. And so what is the same about all springs is their force is proportional to the distance they get stretched. What's different about every spring is that proportionality constant is different. So you'll see as we do the problems, they'll tell you the spring constant. They'll say, hey, the spring constant is, or maybe that will be the problem. Find the spring constant. And so help me out if this is making any sense to you. Would this one represent the red one, the white one, or the blue one? Well, it would be this. Okay, so this is the slope, right? But it's the least slope.
Well, because it'd be the area underneath.
It'd be the red because it stretched further or less force.
Yeah, and so the area underneath it travels more distance to get less force.
Well, how about we look from there to there, which I guess would correspond to, say, from there to there, right? Now, when I was looking at these two springs, didn't I put 500 on here and 500 on here? So wasn't this the same increase in force? Wasn't there the same change in force? So wouldn't that have to correspond to K times the delta X? All right, so as I look in here, I would say that the change in force and the change in force of each of these were the same. Was the change in X the same? Now, wasn't it smaller for the white one? So if this number is smaller for the white one, what does this say about the white one? Doesn't this one have to be bigger? All right, so that would tell me then that this white one has a bigger K, spring constant, than the red one. And as I kind of look here, it might be kind of hard to tell. I don't know, does this blue one look a little smaller than the red one? Yeah, so I'm thinking that the red one then has the smallest K. It has the biggest X, delta X, and they all have the same delta F. So the one with the biggest delta x must have the smallest k. So I'm thinking this corresponds to the red one. It's got the smallest spring constant. And then this one over here would be my white one. That's the one that's got the highest spring constant. And so the blue one is somewhere in between. Okay? And so there's my spring constant. Kind of ran out of room here. Let me erase maybe this graph here. I don't want to leave that. I don't want to erase that equation. So that's what we're working on here, the conservation of energy. But I do want to look a little more at this equation. First of all, K a little bit better. What would the units be? Yeah, did you see that? Newtons per meter? I mean, you want this to come out and to be newtons, and you're going to measure the distance it stretches in meters. So the meters cancel off, and you're left with newtons. And so you'll see that we'll have springs that will look something like this, 100 newtons per meter. In fact, the one we use in lab is at 9 newtons per meter. Maybe I shouldn't tell you, because that's what you're supposed to find in the lab. That's not today, though. We'll do some circular motion today, so that's next Monday. So maybe you'll forget by next Monday. But you're supposed to kind of hunt and look for that and find what's the spring constant of that one. Okay. But again, what does 9 newtons or 100 newtons? I'll stick with the 9. What does 9 newtons per meter mean? Well, it means if I come along and I grab that spring and I stretch it 1 meter, how much is it pulling? 9. What if I stretch it further? I better not do this one 2 meters, but if I pulled it 2 meters, how much force do I get? 2 times 9, 18, right? If I pull it 3 meters, how much force do I get? 3 times 9, 27. You get the idea then that this is an indication of something about how stiff the spring is. How much strength does it have? How much force do you get for every meter do you pull it? So again, seeing this white one, then stretch very little. This has a large spring constant. I get a lot of force for a short distance. And I should do one more step before we finish here, is that the force from the spring is Kx. That's its magnitude. What about its direction? In other words, if I pull the spring down, so it stretches down, which way is the force? Up. If I had turned it around and I pulled the spring up, which way is the force? Down. If I had laid this spring horizontally and hooked it to the sink, and I pull it this way, which I'll call west, which way is the force? East. And so hopefully, without doing too many more, you'll see that to write it as an equation, I probably want a negative sign there to finish it off, saying whatever distance you stretch it in x is then opposite when you the force it. So you stretch it to the east, it pulls to the west. You stretch it to the north, it pulls to the south. You stretch it up, it pulls down. You stretch it down, it pulls up. Okay, it's always going to pull opposite to the direction it stretches. Now I just realized, and I don't have a good illustration for that, maybe I should find a spring. These springs, the coils, are real tight with each other. So you can't really compress them. But some springs look more like this. And not only could you stretch it, but you could also compress it. And so if you could imagine a spring hooked right here, out like this. If I stretch it, it pulls that way. What if I compress it? It pushes back. And it turns out to be the same pattern. So remember this equation, whether you are stretching it or compressing it. A little warning for you. When does x equal to 0 then? Yeah, what we'll call the unstretched or uncompressed, right? In other words, as you start working on a problem, do you have the freedom to pick where x equals to 0? Or has it been chosen for you? Yeah, we're back to that, and I see it as a very common mistake, right? You have the freedom of choice, but once chosen, it now has power over you. So, if you are working on a problem, and you decide to use this equation, don't forget that not only have you chosen to use that equation, you've also chosen where to pick x equal to 0. And you might miss that. And if you miss that, you may choose, oh, I'll pick x equal to 0 over here, which may not be appropriate. And of course, then the problem comes out to be all wrong. And then you're in my office at office hours going, I don't know why this isn't working out. This makes absolutely no sense. And I'm telling you, you had that freedom of choice, and you chose it. And here's where you chose it. And if you don't realize you chose it, that's when you're going to get into some troubles. And so you need to realize where x equals to 0. By the way, with that said, it might be nice to come back to our equation for potential energy. Do you remember where that one came from? Did we pick where y equals to 0? And it's probably too bad I erased it. We didn't, did we? Yeah, some of you see, all we did was pick which direction was positive and which direction was negative. Okay, so if you are going to use this equation in a problem, which I know you will, but just remember that when you pick this equation, you need to know where it comes from. And what you have done is you have now chosen not only that equation, but a consequence of choosing that equation, you have called up positive and down negative. All right, that's not so bad to work with. But notice you also have not chosen where y equals to 0. So you can still choose y equal to 0 anywhere you want. And that will become a powerful tool. It also can get a confusing tool because for gravitational potential energy, y equals to 0 hasn't been chosen. Yet, for the potential energy, and I'm going to use this equation to derive potential energy here in a second. So if I use this equation to derive potential energy from a spring, haven't I then chosen where x equals to 0? Yeah, so slightly different situation. It's why we always go through this. And to be quite honest, it's my belief why there's a lot of failures in the first prototype of any machine built by engineers. It's like, ooh, why did this fail? Oh, well, we use this equation. Well, where'd you get that equation? Out of the textbook. Okay, got it out of the book. Well, where did the book get it? Well, they got it from this integral. I didn't pay any attention to this integral. Really, would you pay, like I said before, would you pay any attention as you are building a second story to how the first story is built? Well, certainly. You don't want to put a lot of weight on the second story. If the first story is made out of balsa wood, it just doesn't make sense to put a pool up there. It's not going to hold, right? It just doesn't have the strength. And so the foundation is very important here. And so that's why you got to step back and say, whoa, 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 where does all this come from? What is the foundation behind it? And you want to make sure you kind of catch that foundation. All right, so you'll see me do that many times, and hopefully even today, but if not today, definitely on Wednesday when we start doing some problems, we start looking at the energies. We're going to look at the potential energies, and I'm going to look at this and say, okay, let's use gravitational potential, energy Y. Where do you want to pick y equals to 0? But then we'll do also in that problem a spring. And we'll say a spring, you got to use the formula. I haven't derived it yet, but you got to use the formula. And I won't say where does x equal to 0. It's been chosen for you. Once I pick this equation, it's been chosen for you. Once I pick this equation, x equals to 0 has been chosen for me. And so I just need to know that. I need to realize where that comes from. Like I said, otherwise we get into troubles. We need to realize, what happens to an O-ring when it freezes. We can't just, who cares what happens to an O-ring when it freezes? It worked fine in the laboratory. Let's just shoot off the space shuttle anyways. And all kinds of troubles can come up too if you don't realize the equation doesn't work down on those. I put it into the equation. It said it would still seal. No, the equation said it was only good from 40 degrees on up, and you are using it at 28 degrees, and you're going to blow up the whole space shuttle. So that's the danger. It's these fundamental stuff, the stuff at the beginning. All right, well, finally we can get to what I was after in all of this. What is the equation then for the potential energy from a spring? It's going to become part of our equation. To get that, we have to do the integral from a spring. And of course, to do that, we needed this here. Okay? So maybe I should draw a picture over here. Let's do this. Since we do have an equation let's take a spring, and this time I will lay it horizontally, so I won't worry about the x-axis. But let's say that it's already been stretched to say here, x initial. And you come along and you're going to pull it to here, x final. And so I'll instead of using A and B, I'll use initial and final. Right? All right, so I'm going to pull it here. And that should equal to your change. So let's put in our equation. Our equation for the force from a spring would be this minus kx. And I guess it would be in the I hat direction. And that's what we meant by this is the equation and its direction. And hopefully it makes sense. Here's what you're saying. If x is a positive number, then what you're saying is this is pulling in the negative direction. Okay, good. And then what I'm going to do is do an integral, and I'm going to pull it in the x direction. And in this case, I'm going to pull it in the positive direction. So my dx is a positive number here. And so there's my di. So there's my, and I guess I need to take a dot product, but those two go together. And so I'm going to go from some initial to some final, some initial to some final. And let's see what I get here. I guess I get a minus kx dx. And so here's that integral I said. It's path independent. We're only going to have to do it once. Great. Won't need to do it again. We'll remember where it comes from, so I know where x equals to 0 is. But what I get then is a negative, a k. I get an x squared over 2 evaluated from some initial to some final. So this becomes 1/2 k, or negative, 1/2 kx final squared minus a negative 1/2 kx initial squared. And again, if we do what we did before, we can compare these together and we can say, let's call this then negative of the final potential energy from the spring, and then this is the initial potential energy of the spring. I think you can see that as we compare positives to positives, we have the initial potential energy of the spring is 1/2 kx initial. The final potential energy of a spring is 1/2 kx final squared. The two of these together are saying that the general formula for a spring then is 1/2 kx squared. And so there's the potential energy from a spring. And I don't think you've seen that, at least in your physics classes. I know we didn't do that in 102 because when we did potential energies, we just did gravitational potential energies. We didn't do elastic. Although, with that said, I think you've seen this because I think you use it in your math class when you do your work energy stuff and you're learning to do your integrals. But again, the focus there is more about math, how to do the integrals, than it is about what does work mean and how are we going to use it, where here it's the reverse of that. But it allows me to finish this over here, and I can say, all right, the potential energy from a spring is 1/2 kx initial squared. Final then is 1/2 kx final squared. Well, there's one more I should do. Wasn't this the force of friction dot dr? Oh, negative. Right. And so in this equation, let's see, we've got 6 of them so far. 1, 2, 3, 4, 5, 6, and now the final one here is the non-conservative force. And as I said, if you're reading along here, you won't find the heat in chapter 7. You're going to find that in chapter 8. So here's where they add 2 our conservation of energy by putting in our non-conservative force. You might be happy to hear that even though you went through chapter 6 and we did those more complicated air resistance ones, we probably won't even touch those here. I mean, let's just do the simplest friction, which was what? Yeah, it was the kinetic friction, right? If something is sliding along, we had our kinetic friction. So my final step here to finish this off, and then 2 other quick things to show you, and then we'll be done with both 7 and 8. We'll get into some examples. But let's do this integral too, so that we now have the full spectrum of possibilities, kinetic energies, both potential energies, and our heat energy. But our heat energy, Q, is minus this integral of the force of kinetic friction taught dr. Now maybe I should pause. Why kinetic? Why not static friction? How much work is done by static friction? Right, the whole idea when you're using a static friction means it's not sliding. If it's not sliding, we don't have any distance, and part of the work had to be with a distance involved here. So if we're only static, if we're not having any sliding going on, there's still no work being done. So you're not going to have any work done by static friction. So there's no point in dealing with or talking about that, other than to mention we don't need it. It's the kinetic one that does have some work. So maybe if I draw a little picture here, and of course maybe somebody's pulling it with a force F, and of course there would be a normal force, and then there would be a downward force mg, but the one I'm focusing on here is the kinetic friction as it is sliding along here. And so as it is sliding along, maybe I will do the magnitude of the frictional force, the magnitude of the distance it moves, times the cosine of the angle between them. Because this minus sign comes into a nice play. The magnitude, as we learned back in chapter 5, is the coefficient times the normal force. The distance it slides, well, I'll just call that a dx if I move it horizontally. This is the interesting one. What's the angle between these two? Do you see it? Yeah, good. It's 180, right? If the box is sliding along this way, the dx is that way. That's the way it moves. The force of friction's the other way. There's the 180 degrees. Now maybe it makes more sense why you see the negative sign in front, because that negative with that negative make a positive. The other nice thing about kinetic friction is it doesn't matter how much you are pulling on it, as long as the normal force doesn't change. And maybe I should put if n is equal to a constant. So in other words, if this was a roller coaster going up a hill that kept changing its slope, I would have to stop right here and say, I can't go any further until I look closer at the path that the roller coaster took. And that's what I was trying to tell you. The best answer I can give you is just to put a K down here and say the heat is related to its kinetic friction, and you got to do the integral for that path. There's nothing more I can tell you other than it's path dependent, so I can't give you a general idea and do the integral for you. You got to look at that problem, and then we got to look at what is the path. But there are a number of cases where what we do is we just pull it along a level ground, or we pull it up an incline, and in that case n becomes a constant, and then we can do the integral, and it actually becomes real easy. It's just the coefficient of friction times the normal times however far you pull it, and I'll call it x there. And so now it's just to the force times distance idea that we learned back in 102 before we knew calculus. Just, hey, force, distance, multiply them together. And so it's just this force, kinetic, times this distance, how far did it move? And so we're back to the easy case. And so hopefully we'll see some easy cases, and I'll tell you we will. We won't do too much in this problem with the non-conservative forces. Even when we get to Chapter 8, this can just get hard enough that we'll wait further on in your education to deal with that. Really, what we're trying to do in these two chapters is get you to use these guys and applying the principle of conservation of energy, not trying to make a hard integral for you to do. Actually, that probably is what you did a lot. I'm guessing. I don't know what you guys did in your math class, but it seems like that would be a good one for your math class because it would force you to do some hard integrals. And that was the point, to teach you how to do integrals. That's not the point here. The point here is to teach you to understand where does the principle of conservation of energy come from, what's the work energy theorem, and how do we apply it to solve some of our problems. So you really won't see any hard integrals. Well, like I said then, this is the whole point of chapters 7 and 8. Let me just erase right underneath it and put this all together now. So here's what we have. We have 1/2 mv initial squared plus 1/2 g y initial plus 1/2 kx initial squared equals 1/2 mv final squared plus mgy final plus 1/2 kx final squared plus heat. Right? And that's what our equation has become for this morning, this first hour. These are all the energies we start with. Kinetic energy, gravitational potential energy, elastic potential energy. Add them all together. What will it equal? It'll equal the kinetic energy that's left over, the potential energy, gravitational potential energy that's left over, the elastic potential energy that's left over, and any heat that might have formed in the process as there was some friction as these things were sliding along. And so there is that same idea carried into the fact that what do we mean by kinetic energy? What do we mean by potential energy? And if they're path independent, you can do the integral, so we might as well write them in terms of their algebra. The Q, that's always the harder one. The Q, well, maybe the Q will be a force of friction times distance. That's what it would be in the easiest case. And that's pretty much what we do. We don't really give you any hard cases. So most likely that's going to be it, but I don't want to say it's always going to be that way. Of course, then the force of friction has to do with the normal force, so we'd have to look at that. Well, there's two other little subtleties here that you may not have caught as we go along here. But again, I'll say it real importantly here. Do you want the answer to all the problems on chapters 7 and 8? There it is, right? That is it. Just fill in the details, okay? Which I know makes it sound easy, and for some of you it will be easy, but for some of you it will not be easy. Some of you will spend hours doing it. And again, hopefully the examples I'll get to here in a moment will kind of set the stage here and get you ready in these next 9 days before the test comes into play. But as I was saying, there's two more little things here that you may not have noticed. What you probably did notice in this chart here is really, for this last hour, I've been doing this. I've been saying, let's focus on energy. Energy will give you two velocities. And I suppose it could be the other way around. Velocities could get you to energies. But could you do this? Could energies get you to forces? It can. Little harder to see. Maybe I'll clear the board right here. We have those over here on that side. But what if I do the following? What if I say the change in potential energy, which is final minus initial, is equal to that negative of F dot dr. And just to make the math a little bit simpler, let's just say the initial potential energy is 0 for a second, just so that I don't have the little delta to float around, and I think that will make things look a little bit easier. And it won't reduce our answer in any ways here. But what we've done this last hour is we've worked with forces to get energy. Could you go the other way around? Could you do energy to get forces? So help me out with this. I know this is your first, I was going to say your first physics calculus-based class, because I know you had 102 with me, but there was no calculus involved. But I'll even do you one better. I bet this is your first calculus-based class at all, other than math and calculus itself. Because if you took chemistry, I don't think it's calculus-based, right? Or biology, or astronomy, and now that I think about it, yeah, so there is some calculus here. So help me out. How are you going to get force here? Do you kind of see it? Do you see you have an integral? Yeah, and so we have to take the derivative, or the anti-integral here, right? We have to undo it. So let's do it. Let's write this as minus, and I better do the dot product first. This would be fx dx, and the second one would be fy dy. So there's our dot product. Remember, x components go with x components, and y components go with y components. So that was our dot product we did last time. But in order to get fx, let's say, what I need to do is to get rid of that integral. And to get rid of the integral, I need to take the derivative. So I'm going to say, let's take the derivative of u with respect to x. Now I'm going to use a notation that may be new to some of you. We like to say this: let's take the derivative of u with respect to x. And what we mean by this funny little symbol is don't treat y as a variable, but treat y as a constant. The fancy word is a partial derivative. And what we're saying is just whatever the equation is for the potential energy, if you take its derivative with respect to x, and if you see a y, just treat it like you would a constant. Just treat it like it was the number 5. Because if you did that, what would happen on this side is you would get a minus f in the x direction. And the other term would become what? Yeah, no change in y. dy is 0. This is a constant. Everything that has to do with y is a constant. And that's kind of the beauty of it. And so rearranging it is saying that the force in the x direction can be found. What you do is you take the derivative of the potential energy. Put a negative in front of it. Now, since the symbol might be new to some of you, if you guys want to write it this way, you are more than happy. That's probably how I'll write it. That's how your author writes it and says, look, since we've got x's and y's, and that's technically multivariable calculus, let's not call it multivariable calculus. That's not a prerequisite for this class. So we'll just say, look, this is what we mean. Take the derivative. Watch, see if it helps. Let's look at the spring for a moment. If I take the derivative of the spring, what was the force in the x direction? Well, let's see. It says minus the derivative with respect to x of the equation for a spring. Well, don't we have the equation for a spring? Isn't it 1/2 kx squared? So let me take the derivative. There's the minus, and there's the 1/2, there's the k, there's the 2x. And so what do I end up with? Yep, Hooke's law again. The force from a spring. Sure, it works. Right? And then likewise, if we had gone through the same math, how would we find the force in the y direction? Wouldn't it just be minus the derivative with respect to y? And like I said, maybe you'd be better off just to write it as a as a regular derivative for now. And so you just say, take the derivative with respect to y. And let's see if that works for gravity. The force in the y direction for gravity then would be minus the derivative with respect to y of mgy. What's the derivative of mgy? Well, it's just mg with a negative in front. And so sure enough, it does work. That's the force due to gravity. And so, yes, it does work. So that's this second part of this that I must admit, we don't do much with this chapter, but we will later on in other sequences. So your author has a little section, and I should point it out here, that it's not just about using work and energy to get velocity. It's also remembering that work and energy can also get you to forces. So forces can go this way to get velocities, or forces can go this way with using work and energy to get velocity, or the other way around. If you know velocities, you can get to work, which give you forces, or velocities give you acceleration, which give you forces, you know. And so we've got a kind of a loop in this puzzle, and so we've got two ways to get to anything in that loop: work, energy, forces, acceleration, velocity. And so we just got to pay attention real closely here to what we're after. So as I said, that was one of two things that your author does kind of at the end here. So there's one. Let me do the last thing, and then we'll just do what I think works best. Is let's do some examples here. Let's see how this is going to be useful here. And this last one is the concept of power. And so what is power? Anybody remember from your other physics class, 102, what's our definition of power? Okay, it is the rate at which the energy is changing. Now wait a minute. Didn't we just say conservation of energy? The energy never changes? So can the energy change? Really? Okay, redistributed is probably a better word. Right. You can't have the total energy ever change, but what can happen is it can go from object 1 to object 2. Or it can change from potential energy to kinetic energy. So yes, it does make sense to look at what rate is the energy changing. So it might be the change in energy per time. In fact, I'll go you one better. It's probably better to say, well, what is its instantaneous rate? How does the energy change with time? In fact, I think your author puts work here, so maybe I should put a W there, the rate at which work is being done. And so if it's positive work, the object may be going faster and faster and faster. And so if this is a rocket and we go to launch it, you know, how much power is in that rocket? That is telling us the rate at which it is gaining energy, which of course would be connected to the rate at which it is gaining speed, which of course is connected to the acceleration. Now, of course, since you noticed how I wrote it, trying to take advantage of your education in calculus here, how would you write the next step? Wouldn't you write it as dw dt, right? And so there's going to be our definition of power. The rate at which work is being done. And so, again, as you can see, the whole point of this chapters 7 and 8 is to get you familiar with energy. But we could talk about the energy. At what rate is a falling object gaining kinetic energy? Or what rate is it losing potential energy? This rocket's going up. At what rate is it gaining kinetic energy? At what rate is the rocket gaining potential energy? At what rate is the fuel energy being consumed? Those are all questions about power. How much energy per time? Which brings me to something that I think you might remember. What units would we then use for power? Yeah, so energy or work would be in joules, and so we would be talking about joules per second. And I heard you guys say a joule per second is called a a watt, and so named after James Watt and his invention of the steam engine here. And say, okay, how many watts is this motor? Be careful. I know that sometimes when people hear the word watts for the first time, or first time in a science class, they think about electrical power. You know, they were just down at Home Depot and bought a 100-watt light bulb and screwed it in and turned it on. And, you know, they're thinking, oh, I'll go get a microwave. And, you know, again, they were Home Depot, you know, and you get a microwave and it says, you know, 1,200 watts. And all these things that are electrical have watts in them. But watts is just a rate of energy. And it could be electrical, but couldn't it also be mechanical? Now, I got to admit, we don't usually think of that in this country, because, I mean, if I go down to the Ford dealer and look at the new Ford Mustang and look at the power of under the hood, it doesn't say how many watts. What does it usually say? Yeah, how many horsepower. So there is a conversion here, and that is 746 watts is 1 horsepower. So if I go back to the old English system, it'll be there. If I go over to Sears and buy a new lawnmower, you know, it usually says on it, you know, 8 horsepower, or maybe that's a little high, 6 horsepower on it. But it's giving me a rate at which this thing can do work. And so there's my connection. So again, we will use the unit of watts for power. And this could be mechanical power, this could be electrical power. Obviously in this class, it's all mechanical power. It has nothing to do with electrical power. That will change next semester, but this semester it's all mechanical power. And I'll do one more final step here. Power then, which is the rate at which work is being done. But work here was a little bit of force and a little bit of distance. And so when I take the derivative, and if the force at that instant anyways is a constant, then I've got force dot dr dt. What would I call dr dt? Well, that's the rate at which it's changing its position. So you can see how that's tied together here. In fact, I think you even have a homework problem, maybe not a tough one, but one that basically is saying, hey, you've got a particular engine in this car, and they tell you how much power that engine puts out. And I don't remember the number. I do kind of remember that it was kind of small. I thought, really? That's a car? Okay. But that aside, this is the power you are getting from that engine. They say you're going uphill, so that's how much force, and you could do your slope and your equations for how much force you need to get up a slope. So that's what you did back in chapter 5. So please don't forget any of the stuff you learned in chapter 5. So you do your free body diagram and you figure out how much force you need to get up this hill. So the point is, they say this is the maximum power you can get from the engine. This is the slope of the hill you want to go up. What is the maximum speed you can go up the hill? And it's pretty small. I guess that's why they have a small power, to go with a small speed up the hill. Or maybe it wasn't a small speed. I shouldn't tell you. I'm not sure exactly the numbers. But I am trying to give you the warning. There is a connection between the force from the engine, the speed of the engine, and the power from the engine. And so what is that connection there? And so you'll be asked to do that. Well, with all that said, probably the best thing I can do now is say, all right, that is all the materials from chapters 5, 6, 7, and 8. Good news is you're not going to get any new material for the next 9 days. Okay? Keep working on this stuff. Let it sink in, and then hopefully everybody will come in next Wednesday and everybody will get an A. Wouldn't that be great? All right. So that's kind of my hope. And I'm sure it's your hope too. Unfortunately, I'm probably sure that you have a lot of other things to do between the next now and the next 9 days. If all you had to do was physics, you probably would get an A. But you are going to have to sleep a little bit. Forget that. Forget the sleep. You might have to eat. Forget that. You might have to work. Forget that. Well, then think about that. You know, look. You say you don't have enough time. Say you don't have enough money. And some of you even say you have too much weight. Well, look. If you don't eat and you don't sleep, you're going to lose a lot of weight and have a lot of time, right? All right, I'm being facetious, obviously, but it's amazing how much time and that would money that would be. All right. Actually, the weight thing would probably be real good for me. I should practice what I say. Huh? All right. Anyways, flipping back here, why don't we do number 2 first? It's a black problem. It's right out of chapter 7. It's one of the simplest ones I can do. It goes right back to the whole idea of work and distance. Maybe I'll continue to leave those up here so you can focus back on here. But here's number 2. Number 2 simply just says here, a raindrop. A raindrop has a mass of 3.35 times 10 to the minus 5 kilograms. It falls vertically at a constant speed under the influence of gravity and air resistance. Now maybe I should pause right there, because to get this mental picture, we've got to go back to chapter 6 here. And so here's my raindrop. It's, raindrop. Should I draw this for a raindrop? I only ask because it's a little misleading. Our raindrops look like that? No, they're circle when they fall. That's kind of a drip that people think because they see that off the end of a faucet or something, and there's that little adhesion to it. But the surface tension makes them round, maybe a little bit oblong when the air resistant hits it, but they don't really look like that. But anyways, there's my raindrop, okay? Maybe the wrong shape, but I'll draw it that way. And that was my challenge. I was like, oh, how do I draw a raindrop? And not confuse you with a baseball, you know. I was like, okay, this is a raindrop, not a baseball this time. So here's my raindrop. And if I were to draw the free body diagram, there would be the force of gravity, mg, and then there would be this resistive force that we were talking about back in chapter 6. Because even though this is a chapter 7 problem, they're giving me an important clue here when they say a raindrop falls vertically at a constant speed. What are they telling me right there? Yeah, constant speed, no acceleration. No acceleration, net force of 0. Net force of 0 means that the resistive force is the same as its weight. And of course, it means its acceleration is 0, which means it has met its terminal speed, which, by the way, is probably a very good thing because raindrops then fall at a certain terminal speed. If they fell from 10,000 feet without air resistance, how fast would they be going? Yeah, you would kill everybody down on ground here. So the air resistance is important here that we have it in the raindrops fall at the appropriate speed. And of course, then their terminal speed would be based upon their size. And so you've probably noticed that in your lifetime, particularly today. I mean, today you wouldn't even call them raindrops as much as you would call them, what, fog or mist out there. And I hear the foghorn going on there and out on the harbor. But they're very small, and seems like they're barely falling. I mean, if I look at the ground, it's wet and it's dewy. But as I sit there and I watch them come down, you know, it's just the slightest movement makes them go up and get away. They're very small. They're very low terminal speed. But when the heavy rains hit, I see a big difference. They're coming down pretty hard. And when the raindrop gets bigger, I don't like to get hit by those. I don't mind walking through the mist or even the light rain. But the big ones, or if they then turn to hell, which, you know, then they're really coming down hard here. So anyways, but I guess I digress back to chapter 6. So there's the idea. You got to have that first good physical picture of what's going on here. So hopefully that's in your mind first. So that's what they gave away for our clue, relying on us to go back. They also gave us our mass, so I might as well put that in there, 3.35 times 10 to the minus 5 kilograms. So there's the mass of this raindrop. But here's what it says. As it falls 100 meters, what is the work done by gravity on the raindrop? B. Oh, no, I'm sorry. They paused there. If it falls 100 meters down, what is the work done on the raindrop? A, by gravity, and then B, by air resistance. So they're looking for the work. And so there would be a part A. There would be a part B. The beginning of chapter 7 said work was the integral of F dot dr. Here, the work, same idea, work is done by the integral of F dot dr. In this case, what we're going to do is we're going to have the raindrop fall 100 meters. So let me just write this as the magnitude of the force times the magnitude of the distance it goes down times cosine of the angle between them. And so in this case, it is a force of mg. It is going downward and labeling that as a positive number, absolute value. It's 0 to 100. It would be cosine of 0 degrees, right? Force is down. Which way did it move? Down. What's the angle between two vectors pointing down? 0. Okay. And so what I get is an mgy evaluated from 0 to 100. And so there would be my work done by gravity. Yeah? Well, so there's two ways to do this dot product. Let me come over here, and because I think that's really what you're asking. You're asking about the force being negative. And so you could do this integral by saying it is a negative mg in the j hat direction. And so there's your force in the negative direction, dotted with the movement it makes. Well, it makes a movement in the negative j hat direction. And so the two negatives cancel off, and you get mg dy. Okay? So if you put a negative here, fine. Just don't forget it over here. What did I do? I did a little different. I did a dot product that said it was the magnitude of the force times the magnitude of the distance times the cosine of the angle between them. So once I do magnitude, I have to pick a positive number. I have to pick a positive number there. And so that was our two forms of dot products, either putting the components together or by putting the magnitude and cosine of the angle. So either way, you get the same integral as mg dy. So, good question, and I'm glad you see it. Because you can get yourself confused if you do it half of this and half of that. You'll get a negative sign and mess it up. I'll even do you one better. I thought you were going to ask this. I thought you were going to say, well, isn't the work the negative of the potential energy? And isn't the potential energy a conservative force? And didn't you already do the integral? And didn't you tell us to use that one because then you wouldn't have to do any integral? Wouldn't that be better? Okay, yeah, that's a good question. I'm glad you asked it. Right? So if you want to do it that way, sure. This would be a negative of the change in potential energy. And so it would be final minus initial. And so my final might be mg0. My initial would be mg times 100 meters. And so sure enough, I get the same thing whether I do it any of these three options that I've put in front of you. So integral with a dot product this way, integral with a dot product this way, or avoid the integral altogether, since we know that was the nice thing about conservative forces. Set the work equal to negative of the change in potential energy, calculate the potential energy, since we have those formulas, and then plug and chug and come up with this. Okay? So either way you want to do it, you're going to get that number. Let me put the numbers in here. The mass was 3.35 times 10 to the minus 5, if I remember right. Good. Times G, 9.8 times 100. And it's not a big number. It is 0.0328. And what are the units here? Joules. Good. This would be the kilogram meters per second squared times another meter. And that's a Newton times a meter, and that's the joule that we were introduced to at the beginning of chapter 7. And hopefully one you remember from the 102. So all work and energy are measured in joules. So again, as our first example here today, this would calculate the work done by gravity as it moves down. In fact, I'll jump back to a positive number or a negative number. Positive. What does positive numbers tell us in terms of work? Yeah, that by itself would want it to go faster. And doesn't that make sense? The force of gravity by itself would want to make it go faster. Now I have to throw in there by itself, because is that the only force on this raindrop? No, now there's the air resistance, which is what part B is. Part B is to calculate its air resistance. Fortunately, B is a very easy calculation now that we've done A. Because as you told me already, back here when we did the free body diagram, isn't the resistive force equal in magnitude to mg? So I will put mg for its magnitude, I will put down in its magnitude, and I will put cosine of, do you see the 180 here? Because the movement is down, which way is the resistance? Up. And those two vectors are opposite. So taking a dot product like this, it looks a lot like we just did, except in having cosine of 0, I have cosine of 180, which basically means I'm going to get the same formula I got here, but with a negative sign. And so I have a negative mg times 100 meters. Now again, hopefully that doesn't surprise you if we had done it the other way. If we had done it like you were asking about this, what would be different, and I'll change it here in red, but I would have this force be a positive direction. But the movement is still down, and so I would get a negative here, and so the work done using the components for my dot product is the same thing. So again, whether I want to do the dot product by doing magnitude, and cosine of the angle, or whether I want to do components, I should come up with the same thing. I'll even give you one more better here. The work-energy theorem. Didn't we say that the total work is equal to the change in kinetic energy? And to be quite honest, I think this is what the author might have been after. He said, look, now that you've already done a calculation in terms of work, let's look at it and how it might be useful. Just to do it again is not very useful. But what is the change in kinetic energy as this raindrop falls? Isn't it 0? Don't they say no change in speed? It falls at a constant speed? And so as this raindrop is falling, so of course that means it fell from further up to get to its terminal speed. But when it was at this point, it's at its terminal speed, and it keeps going at its terminal speed. And so the change in kinetic energy is 0. So doesn't that mean the work done by gravity plus the work done by the air friction, I'll put a little r for air resistance, equals 0. So doesn't that mean the work done by air resistance is negative the work done by gravity? And so whether we go back to forces or whether we go to the work energy theorem, it all comes back to really A, that this would then be a minus 0.0328 joules. So the work done by gravity is positive, the work done by the air resistance is negative. You already told me the positive number by itself would mean it wants to go faster. So gravity by itself wants it to go faster. The air resistance is a negative work. It by itself wants it to make it go slower, right? Negative work. The two together is the final result. The two together, since they are equal and opposite, give you a work of 0. What does work of 0 mean? Yeah, no change in speed, no change in kinetic energy, not going faster or slower. And that's how they all tie together. So I know it's a black problem, but I like it as a good first illustration. I think it shows the point really well. Well, let's try number 22. Number 22 elevates us to a blue problem now. And it also illustrates this idea of the work energy theorem from the standpoint that the force is not a constant. Because as I told you about an hour ago, if our forces are constant, I'm not sure there's much to be gained by going through energy. I mean, constant forces are not hard to work with. They give you constant accelerations, which give you easy sets of equations to work with. But the non-constant force, which gives you a non-constant acceleration, those can be pretty hard, especially if you're trying to do an acceleration which is based upon time, but you only know forces based on position. That's where it could be really hard. And that's why this is such an easy approach. Hopefully you'll see that. Because we wouldn't want to approach this problem with acceleration. It involves time. And, excuse me, we, as you'll see in this problem, know about forces and distance. Watch, look at number 22. 22 says, a 100-gram bullet is fired from a rifle having a barrel of 0.6 meters long. Okay, so this is the length of the barrel. Choose the origin to be the location where the bullet begins to move. Then the force in newtons exerted by the expanding gases inside of the barrel is given by this equation. 15,000 plus 10,000 x minus 25,000 x squared, where x is measured in meters. A, determine the work done by the gases on the bullet as the bullet is traveling the length of the barrel. B, what if the barrel was now 1 meter long? How much work would be done? And how does this value compare to what you got in A? All right, so again, did you read it all the way through? Got the first idea of it, the first reading? Come back, draw a picture, think about it, read it in detail. Do that step one. Got a good physical picture of what's going on. So as I go back and read it a second time, let's see, I've got this barrel. Okay, so there's the barrel. They tell me the barrel has a length of 0.6 meters. Okay. The measurement is that back here somewhere. What does a bullet look like? I guess it's a piece of lead kind of jammed in a shell with a bunch of burning gases inside. Firing pin, trigger. Okay, there's looks like a snow cone more than a bullet there. Okay, but so this piece of lead is jammed into the shell. The hammer is drawn back. The trigger is pulled. It goes in, ignites the gunpowder, and it starts burning. Okay? And here's what they say. They say that as the bullet is going down the barrel, it's got a force, if I remember right, of 15,000. So 15,000 plus 10,000 x minus 25,000 x squared. And so that's just the equation. They just give that to you. They say X is measured in meters. They say force is measured in newtons. They say the origin is measured where the bullet starts. Okay, so they've given us that equation. And I'm not even sure you have to study the equation, but we probably should. I always feel better if I understand the physical problem in much more detail. It's a little bit work up front, but it saves me from problems later down. It keeps me from doing the wrong things. So before we even start answering the question, which is how much work is done on the bullet from these expanding gases, let's see if I even just understand the whole idea of the forces a little bit better here. I mean, maybe I'll just start with the mathematics. I mean, what would a graph of force and distance look like here? It's a parabola. Which way? Concave down, right? Okay, so the math is telling me it's concave down. Where is the parabola centered? I mean, what does this thing look like? Okay, so at x equals to 0, you can kind of see it's 15,000. And as x increases, it must look something like that. So there's my parabola. And of course, I guess this would be the other part of that equation for negative x's, but we don't need negative x's for our problems. So maybe we should examine this a little bit. Why the 15,000? Why the linear term that makes it get bigger? Why the quadratic term which makes it go concave down? Well, maybe I'll start with this first one. Why at x equals to 0 does it already have a force? Yeah, so what we have is we have burning gases in there. This bullet is jammed inside, and so pressure is building up and building up and building up, and the bullet hasn't moved yet. The bullet doesn't move until it overcomes that static friction, right? So there's a static friction between the lead and the shell. Once it comes enough, now it breaks free from the shell. Okay? And so by that point, the pressure has built up enough inside here to somehow justify this 15,000. So there's my initial force as it comes off. And so there's my 15,000. But notice then that as it goes down the barrel, doesn't the force increase? Why? Yeah, the gas is still expanding. There's still more pressure building up. This stuff is still burning. And the bullet isn't moving that fast. So all these molecules that are getting real hot behind it are just, you might say, going faster than the bullet itself. But at some point, the force reaches a maximum and begins to go down. Why less force? Yeah, and at that point, I would say, you know, the bullet, maybe the bullet's here. It's going pretty fast. And so now I would say those gases, number one, have probably stopped burning. And so as they expand, they're not catching up quite as quickly, but it's still a positive force, so there's still a lot of pressure in there. Could I get a negative pressure? No, I wouldn't even go as far as they're cooling, but they are doing that too. But putting that aside, what we call adiabatic expansion, which we'll deal with next semester. Let's say they don't cool down. It's still why would I have a negative here? Right. And the bullet, at some point, could be going so fast that it's moving faster than the expanding gases. And so the gases aren't pushing on it anymore. What's happening is the atmosphere now is pushing back on it. So as you said, a vacuum is being formed inside there and pulling it back, which would obviously then be slowing the bullet down. And where on this graph would the bullet be going the fastest then? Would it be here? Would it be here? Yeah, this is where it's going to get its maximum speed. See, I know the force is smaller here, but isn't it positive? Isn't it still making it go faster? Not by much, not as nearly as much here. So here's where the force is the most, and here's where the acceleration is the most. But over here, there still is an acceleration. There still is a force. It still is going faster. Not by much. So I would say most of the speed occurs here. This last part is not as relevant to get the overall speed. So we'll notice that in this bullet. I'm hoping that the bullet is long enough but short enough. What do I mean by that? Well, long enough that I can get at least significantly far on this graph. Maybe all the way to the end, because that would be its maximum speed. If the barrel was longer than that, what would happen? Now it would slow down. So I don't want my barrel too long here. Otherwise, it's going to start slowing down the barrel instead of. Oh, and we're out of time, aren't we? So, all right, so on Wednesday, we will get started there. Yeah, but hopefully you're done with Chapter 6. Turn it in. If you're not, keep working on it. I know these can be hard ones, but don't let it get in the way of your 7 and 8 either. Okay, but big thing is not the homework today. The big thing is, are you ready 9 days from now? That's the big thing.